Today we're going to look at the derivatives of some exponential functions, and the way that we're going to do this is we're going to use logarithms. So just a reminder, the relationship between exponents and logarithms is that they undo each other. So if I take the logarithm of an exponent and the base of our log and the base of our exponent should match, then they undo each other. I just get x back again. So the natural log of e to the x is just x back again. Similarly, if I have a logarithm and I raise that as an exponent to my base, again, the e and the natural log undo each other, I just get x back again. So we can use this to help us solve a couple of derivatives that so far we don't have the tools to do. So for instance, let's find the derivative of 3 to the x. Now you might be tempted to use the power rule, but remember the power rule would be if this were x cubed, right? The power rule is what happens when x is the base of our exponent. But here, x is the power of the exponent. What do? Well, our issue here is that we can't do anything while x is up in a power. So we're going to try to get x back down again. How are we going to do that? Well, let's think about this function in terms of y equals 3 to the x. What can we do to make this so we can use logarithms, right? Well, if we think about it, e to the natural log of 3, the e and the natural log cancel each other out, which just leaves 3. So I can replace my 3 by e to the natural log of 3 and raise that to the x. Now, if I raise a power to a power, I can just multiply those powers. So I could rewrite this as e to the natural log of 3 times x. Okay, now why is this helpful? Well, now if I want to take the derivative, I now have this in terms of e to the x. E to the x is the only thing where x is in the power that we actually know the derivative. What's the derivative of e to the x? It's just itself. So I can use the chain rule here. Now, for the chain rule, we need an inner function and an outer function. Our outer function in this case would be e raised to some power, right? In this case, our power is natural log of 3 times x. That's our inner function. So our inner function is the natural log of 3 times x. What's the derivative of the natural log of 3 times x? Well, the natural log of 3 looks funky, but it's just a constant, right? It's just a constant. So here we have x to the first power. If we take the derivative, we're just left with the coefficient. So the derivative of this is just the natural log of 3. Yeah? Okay. So if I want to take the derivative of both sides, I've got y prime equals, so again with the chain rule, we take the derivative of the outer function, in this case it's just itself, e to the natural log of 3 times x, that's a multiplication sign, and then I multiply it by the derivative of the inner function, which is natural log of 3. Okay. Now, this is a little bit messy still, but I can notice here that the e and the natural log cancel each other out. So I can just rewrite this as 3 to the x times natural log of 3. All right, so that's how we would find the derivative of this. We're using the chain rule, and we're using the fact that logs and exponents undo each other to find the derivative when x is our power. Okay, so this works for any base. So if I have any base that's positive and not equal to 1, then my derivative is the natural log of that base times the function itself. Yeah, just like we did up here. Okay, so now what happens if we know what to do if x is the base, right? If we have something that looks like x cubed, and we know what to do if x is the power. So if we have something like 3 to the x, what do we do if x is both the base and the power? So if we have something like x to the x, what do we do then? So again, I want to take care of this x as the power. Up here, we took care of x as the power by raising e to the x, right? Now what I'm going to do is I'm going to try to get the x out from being a power. So how are we going to do this? Again, let's say this is equal to y equals x to the x. And How do I get x down? I'm going to take the natural log of both sides. So I've got the natural log of y equals the natural log of x to the x. Now, a property of natural logs is that if I have a power inside a natural log, I can pop that power out to the front. This has to do with the fact that natural logs are undoing exponents. So we've got x times the natural log of x. Okay, so now we don't have x as a power anymore. Now we can take the derivative of both sides. So we're going to do this using implicit differentiation. So here we're going to take the derivative of both sides. Technically, that's the derivative of the inside as well. All right, we take the derivative of both sides. What's the derivative of the natural log of anything? Just 1 over itself, right? And then since this is implicit differentiation, since we're trying to find this with respect to x, we also need to remember to multiply by that dy dx. All right, now this is a product. I need the product rule. So I'm going to keep the first function and multiply it by the derivative of the second function. So the derivative of natural log of x is 1 over x. And then I add to that the derivative of the first function times the second function. Yeah? All right. Now what do? I've done my implicit differentiation step. Now I want to solve for dy dx. How do I do that? I can multiply both sides by y. So I've got dy dx equals y times this whole thing. And let's simplify this a little bit. X divided by x is just 1 and natural log of x. So I've got y times 1 plus natural log of x. Now, it would be nice if I didn't have this in terms of y, if I only had this in terms of x's. But in fact, I know what y equals, right? Y equals x to the power of x. So this is x to the power of x times 1 plus the natural log of x. All right. So to recap, we've seen that taking advantage of the fact that logs and exponents cancel each other out, we can find derivatives where x is the power, and we can find derivatives where x is the base and where x is the power using a combination of chain rule, implicit differentiation, and clever applications of the natural log.